Let us continue our exploration of waves in the optical system. We are in the 10th week and this is the 4th lecture in this topic. In today's lecture as well, we are going to stick to the limit of being able to describe waves through rays, and also we will stick to paraxial approximation. Unless there is a reason for the ray to get refracted within a given medium where the refractive index is a constant, the ray basically traces a straight line. So, which means that I need to worry about ray deviating from the straight line only at points where refraction takes place. So, I can map this and rewrite this entire problem elegantly using matrix methods, which is what we are going to do in today's lecture. So, I am going to do the following. One is very briefly introduce how would a matrix method work, in the sense that what matrices are and so on. Again, matrices is a very interesting mathematical object. In case you want to get a more deeper feel for what it is and have no idea what it is, better to consult standard linear algebra textbook or chapters on matrices in standard mathematical physics books. So, we are going to use matrices in today's lecture, and as I go ahead, let me also remind you the sign convention. Once again, positive side from O is going to be plus for distances. Similarly, the negative sides is going to be minus for distances, and I have also indicated the convention for angles. Here the angles take the sign of their tangents. With that, let me step back from optics, physics, everything, and just introduce the idea of matrix. So, I am going to do a very limited job here, in the sense of trying to tell you how matrix is a little more elegant way of representing a transformation. Again, matrix is very useful in many other contexts as well. This is not the only place where it is useful. It is really a beautiful way of looking at certain kinds of things, but still for our purposes we look up to it as a transformation. Here I have written for you two equations. So, if you look at it, it will look like two equations with two unknowns. So, if you treat y1 and y2 as unknowns and a11, a12, a21 and a22 are some numbers, then it is precisely nothing more. Here I have written the same equation in matrix form, and if I give names like this, let me call it by capital X, this vector x1, x2, and let me call this matrix capital A and this vector capital Y, then the corresponding equation written in very compact matrix notation would be. So, this assumes that we know how to multiply a matrix with a vector or a matrix with a matrix. So, here what is involved on the right hand side is multiplication of a matrix with a vector. So, y1, y2 is a column vector, and I have this matrix A, which is a11, a12, a21, a22. And this product of this matrix A and this vector y is nothing but what is here. Let me also write y1 and y2 in terms of some other variable, let us say z1 and z2. Now, I have this two sets of equation y1 and y2 written in terms of z1 and z2, but now let me also write it as a matrix equation. So, the same set of two equations now I have written in the matrix form. Again I write it in a compact notation, y is capital B times z. Now, I can substitute for y from here. So, x can be directly related to z in the following way, x will be. So, here when I write A into B, I should know how to multiply these two matrices. So, here I have written the product of two matrices, capital A and capital B. The basis of treating rays using matrix methods is actually shown in this diagram that I have just drawn. The ray between P and Q, or even a little further, can be described by the quantity x1 alpha 1. So, x1 is the height of that point from the axis of your optical system, and alpha 1 is of course the angle that it makes with the horizontal. At Q, you could characterize them with pair x2 alpha 2 for the same reason. It is equivalent to saying that straight line can be characterized by just two numbers, one the intercept and other is the slope. So, every time there is a refraction, then you need new set of such pair of numbers to describe the ray. We are relating one set of x1 alpha 1 to another set of some other pair of numbers whenever there is a refraction that is taking place. So, just as we did a little while ago for the case of matrices, so I had one set of x being related to y, that is x1 x2 related to y1 y2, and then I had y1 y2 related to z1 z2. So, in this case I can directly relate x to z. You could in general see such transformations in rays as only two things. One is there is a translation, that ray goes from point A to point B. So, that is translation, no refraction involved because we assume that it is in a homogeneous medium. But in principle you can have refractions as well. We need to know how to describe translation, we need to know how to describe refraction, and if all this can be done using matrix language, well and good, then we could elegantly handle all these within the framework of matrices. To obtain a matrix form for translation, let me refer back to this figure and also indicate this distance by capital D. So, let us say my ray goes from point P to point Q and the distance or the horizontal distance that it travels is d, and there is also a vertical distance that it has traversed, which is x2 minus x1. And in general we have taken these two angles to be different, alpha 1 and alpha 2, but if the medium is homogeneous, we know that alpha 1 has to be equal to alpha 2. So, as I said, in a homogeneous medium, alpha 1 is equal to alpha 2. Now, from the geometry of figure, I can write an expression for x2 in terms of x1, and if we stick to paraxial approximation, this would simply become, I introduce a variable lambda 1 which will be mu 1 times lambda 1 and lambda 2 is mu 2 times lambda 2. Let me introduce a variable lambda 1 which will be equal to mu 1 times alpha 1 and also another variable lambda 2 which will be equal to mu 2 times alpha 2. We have already said that we are working with homogeneous medium, in which case mu 1 is equal to mu 2, alpha 1 is equal to alpha 2, and hence lambda 1 will be equal to lambda 2. And let me also write the expression for x 2 which will be x 1 plus d times alpha 1. Now, if you see the left hand side of this equation, it is x 2 and lambda 2 which relates to the second point Q, and on the right hand side is everything relating to the first point P here, which is x 1, alpha 1 and lambda 1. So, essentially I have written information about the second point Q in terms of parameters of the first point. Before I write this in matrix notation, let me also make one change here. I can write alpha 1 as lambda 1 by mu 1. So, let me replace this alpha 1 by lambda 1 by mu 1. So, this gives me the relation between x 2 lambda 2 and x 1 lambda 1 and it is now written in matrix form. So, you can think of this matrix that I have written down here as a matrix that represents translation. So, it represents translation of a ray from a point that is described in terms of x 1 lambda 1 to another point which is described in terms of x 2 lambda 2. If I call this matrix T 1, then you will notice that the determinant of T 1 is equal to 1 itself. Here I have a refracting surface like I have shown in black line, and red line represents the axis. Let me call it by P, the point at which refraction of the ray takes place. So, let me blow up this part and draw it here, and let us say that this is a line that is parallel to the x axis, and let us say that this is the incident ray and this is the refracted ray. And now, let me also draw the normal at this point. So, our aim is to relate x 1 lambda 1 to x 2 lambda 2 like we did for translation. We are going to do that for refraction as well using all these angles. So, at point P, what we need to do is to use the law of refraction. At point P, mu 1 theta 1 is equal to mu 2 theta 2. So, remember that we are going from one medium to another. So, this will be medium mu 1 and on right hand side it is medium mu 2. So, what I have done is to assume paraxial approximation and write the law of refraction. Mu 1 theta 1 is equal to mu 2 theta 2. Theta 1 is simply this entire angle here which I am now showing in red, and that is equal to alpha 1 plus phi 1. So, that is my first of the equations. Theta 1 is phi 1 plus alpha 1. It is easy to figure out that theta 2 is simply phi 1 plus alpha 2. So, I have these two equations for theta 1 and theta 2. One another quantity that I will need is the radius of curvature. So, let me extend this back here. This will go to the center of a circle of which this curved surface is a part. Hence, this is going to represent for me the radius of curvature r. And let me also drop a perpendicular here to this point and call this as x. If you take the paraxial approximation, the distance between this point here and this base point here would be so small that you can take the distance from this first point to C as r itself. In that case, phi 1 will be equal to x by r. So, we replace phi 1 in terms of x by r. If I do that, I will get the following relation. Now, you can recognize that this quantity here is simply what we can call the power of the refracting surface, in which case I could write this as. So, if you remember the relation that we got for translation, you will notice that we related lambda 2 x 2 to lambda 1 x 1. How do you get that distance from the axis in this case? So, go back to this figure that we drew for refraction. You will notice that there is only one of them, in the sense that there are no two different values, there is no x 1 and x 2. Instead, what we have is at the point of refraction there is only one height or one distance from the red line, the axis. So, which means that in this case x 2 and x 1 are exactly the same. So, I am going to have x 2 being equal to x 1 itself. So, now I have this form for matrix form for refraction. So, it tells me, like if I start a ray which is described by x1 lambda 1, after refraction what happens to it? So, it is described by x2 lambda 2, and how are they related? They are related by this equation. Specifically, the important part here is this matrix, which gives you the effect of refraction. Now, you can trace rays across several lenses, refracting surfaces of various kind, but you know that whatever be the complexity of your optical system, it is either a translation or a refraction. So, now we have isolated the effect of translation, isolated the effect of refraction. So, all I need to do is to look up in what sequence they occur, translation and refraction, and just multiply the appropriate matrices, and I can very easily get the final effect. If I call this matrix S, then determinant of S is 1 in this case as well. So, what is left now is to do some examples, and we shall proceed with the examples in the next module.